Okay, so once again, guys, you need your books open to 1058. You need your equation sheets turned over to the page 4 side, which is where we see the equations for gases, liquids, and solutions. And so, guys, to put this in context for you, because I think we're realizing that context is important. Today what we're going to do is we're going to talk about mixtures of gases. Without going back to the experience we had on Thursday, one of the notes that I've made to myself is don't turn my lab class loose on the lab until this happens. Because guys, you are going to find that while I know we've laid to rest some of the misconceptions, miscommunications that we had on Thursday, I think you're going to find this both illuminating and at the same time confirming of what you now understand. So this is what should have happened prior to you digging into this lab. So guys, what we're going to talk about today is we're going to talk about mixtures of gases. Understand that we've had this conversation prematurely because I incorrectly thought we could dig into the lab without having had this conversation with a couple simple explanations, which while that was true, it was really the communication issues we needed to deal with first. So the beginning of this is going to feel very familiar, and it should, because it's all about what we've talked about pressures contributing to total pressures when we have mixtures of gases. Then guys, what you're going to find is that we're going to take that thought and we're going to first of all expand on it, and we're going to talk about a ratio that exists between moles of gas and pressures of gases. I'm not sure if I'm going to try to make the connection back to the lab. I may. We'll see how the conversation goes. And then from there, guys, we are actually going to, if you want to look at the AP equations, thank you. If you want to look at the equation sheet with me, today to finish the day, we're going to look at the second equation down. It brings in an interesting new idea, which is called X sub A, which is actually what is called a mole fraction. And that's how we're going to wrap up the day, by relating what are called mole fractions to pressure ratios, which is really just an extension of what you're about to learn first. You guys ready to go? All right, here we go. So, guys, when we talk about, and you understand, when we talk about mixtures of gases, we need to talk by defining some terms, and this is what is called Dalton's law of partial pressures. And you do want to write this down. This isn't just a subheading. This is actually the first thing in your notes. So, this is the same John Dalton that you may remember from last year. If you remember last year, we did that assignment where you looked at Dalton, then Thomson, then Rutherford, then Bohr, or Millikan, then Rutherford, then Bohr, then Schrodinger. Exactly, and that was, I don't know if you remember this, but that assignment, it was like a grid, and you filled in the columns, and it said what was their experiment, what did they discover, and then what did they believe atoms looked like. Maybe a stretch for you to remember. But guys, that's the same John Dalton, and if you remember in that picture, when I drew Dalton's experiment, I just drew balloons, because Dalton studied gases. Well, along the way, and remember, Dalton just thought atoms were little solid permanent things. The billiard ball model, remember that? Okay, anyway, it doesn't matter. Guys, this is one of the things that Dalton proposed about gases. And this was in fact true. This is stood the test of time. This is one of his fundamental understandings that actually is true and persists today. The idea is this, that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. Now guys, the book represents this one way, the AP equation sheet represents it another, the difference being number versus letters. So in our book, it represents it like this. It says that P total is equal to P1 plus P2 plus P3 ... You'll notice the AP equation sheet does it differently, so it may be worth glancing at. The AP equation sheet, given that third equation down, it just says P total is equal to PA plus PB plus PC. You okay with the idea? I would always go with the equation sheet. Maybe what I should do is just change this, and then, because you guys probably would have never even noticed that the book did it differently, right? So let's do this, and then we'll all be fine. Are we okay? Is that sort of the way it's represented? Oh, it wrote out the word total, but we're good. Okay, so guys, what then does this mean? And again, let's let sleeping dogs lie. I don't know what that, it's like hell in a handbasket sleep. I don't know what either of those means, but I think what that means is this. Let's not get crazy about this, but let's revisit what we've agreed we understand. So guys, the idea then would be this. Here we have two samples of gas. We have again, a red gas and a blue gas. This is not the lab. This is not butane and water. We're not making those close connections. But we've got two samples of gas. So, what is the same about these gases? Well, their volumes are the same, right? Circles are the same size. Let's pretend like their temperatures are the same. So, guys, if all of those things are true, if their temperatures are the same, if their volumes are the same, let's then talk about what their pressures would be. How would the pressure of the blue gas relate to the red gas? Let's count. It is greater, but we can do even better than that. And these are the kind of things they will enjoy showing you on the AP test. So we've got 5 of these, we've got 10 of those. So what will the pressure of the blue be relative to the red? Twice. Guys, the understanding is this, that if PivNert is in fact true, and it is, if we can say that these have equal volumes, and if we can say that they have equal temperatures, and R is a constant, if we double the number of moles, we will effectively double the pressure. Do you get the idea? Okay, so with that in mind then, with the understanding that we're going to say that the pressure of blue is twice that of red, the question then becomes this, and again, I can only do this by taking us out of presentation mode. So let me zoom in a little bit. Because what happens when we do that? When we mix them together, what happens to the pressure of the red gas? Doesn't change. What happens to the pressure of the blue gas? It doesn't change. But what happens to the pressure inside the cylinder? So let's say if red was 1 and blue was 2, now it's 3. Is that okay? So guys, that's the fundamental idea, is that if the pressure of red is 1, and let's say atmospheres, if the pressure is 1 and the pressure is 2, when we mix them together, then we understand that the pressure is now 3. Their pressures add up, and then what would the volume of blue be? The same, and the volume of red? The same. So they behave as if the other's not there, but their pressures are additive. Do you see why this would have been better prior to the lab? Huh? All right. Yeah, and you guys good with the idea? Okay. Now, guys, we're going to learn something interesting. Whether or not we relate this back to the lab will depend on how this conversation goes. I'm thinking I'm going to risk it. I'm a little gun shy, but let's see what happens. Okay, so we're all in agreement with this, right? Okay, now, guys, don't try to do this math with me, but we're about to learn something interesting about these mixtures of gases. And then we're going to come back to our ball thing that I just did. Okay, so here's what we're going to assume. We are going to assume that these are ideal gases. And if they're ideal gases, what equation dictates their behavior? PivNert. So here's the idea. We've got PivNert, yeah? Okay, let's solve that for Pa. So guys, if we solve PivNert for pressure, we end up with NERTVA. Okay? Now what we're going to do is we're going to take this P and we're going to plug it in for all of these P's. You get the idea? But guys, understand that P is equal to NRTVA. So we can rewrite Dalton's law of partial pressures as NRTVA plus NRTVA plus NRTVA. Get the well, and that's what I'll show you why we did that in a second. So do you understand what we've, and maybe we're happier here, we'll call this A and B and C. Do you understand the little mathematical manipulation that we just did? And that's the question. Why does just the N get the subscript? And the answer is this. Guys, imagine that we're going back to our previous example. Do I dare go back there? Can you picture that when we brought the two balloons together? So guys, R is a constant, right? So we can factor that out. What do you know about the temperature of all the gases in a mixture? It's the same. What do you know about the volume of all the gases in a mixture? They are also the same, which doesn't mean they cancel out, but it does mean they factor out. So functionally, what we could do is this. We could say that pressure total is equal to RT divided by V times N1 plus N2 plus N3. That's not a 3. Plus, oh baby. Yeah, well, that shouldn't be a line. But guys, do you see what we're saying here? So what we're saying, and Brandon, to answer your question, why is it just the moles, the N's, that get the subscripts? Because that's the only one that's different in a mixture of gas. When we're solving for pressure, guys, the R, the T, the V is the same. So now we're going to say something important. This ratio relative to pressure creates a this relationship between pressure and number of moles creates a ratio that is balancing, if you will. Let me show you what that means. So guys, before we transition, what we're saying is this. There is a relationship between pressures and numbers of moles. Because R and T and V are constant, there's a ratio relationship between numbers of moles and pressure. So guys, check this out. Here's the idea. I'm going to clean this up, and now we're going to go back over here, and now let's talk about the relationship. I think I can, okay, we can do this. So let's go black because it doesn't look like blue or red. So guys, here's the idea. So what do we know about the number of molecules in here compared to there? Blue to red, twice as much. So let's call this 2 moles, and let's call this 1 mole. Is that okay? So it's twice as much, 10 to 5, 2 to 1, twice as many particles, whether it's particles or moles, twice as many moles of blue as red. You okay with that? Now guys, what did we also say about pressure? Which will have the greatest pressure? The blue guy. So what if we maybe then call this 2 atmospheres and 1 atmosphere? And guys, again, it doesn't matter what the units are, it could be torrs, PSI, doesn't matter. We know that the pressure of this will be twice that. And are you comfortable with why we know that? How do we know that? Says who? Says says Pivner, right? Pivner would tell us that if all other things are the same, doubling the number of moles will double the pressure. Is that okay? Okay, so, and guys, this is where I run into problems because I can't manipulate this, so I'm going to have to get out of presentation mode, which is really going to screw up the orientation of, that's not horrible. Let's see if I do this. Get rid of, oh yeah. Ooh, this is going better than I thought. Okay, so are we okay with this? Okay, now guys, let's talk about the bringing together of these. So when we bring these together, now, how many total moles of gas do we have? 3. and I'll label it, 3 moles. What is now the total pressure inside the cylinder? 3 atmosphere. Says who? No. Says who? How do we know the pressures are the same? Dalton's law, and you could do it with Pivnert, but our most direct route is Dalton's law of partial pressures. The pressures are additive. So now, guys, look at what we know. When these mix, we've got 3 moles of each, right? When we separate them, I don't know which one this will let me grab first.
3 moles of each or 3 moles total?
Oh, gosh, thank you. 3 moles total. So, yeah, thank you. When we separate these, now, guys, look at the ratio. Mixed together, we've got 3 moles. Separate, we've got 2 moles. So that means in the mixture, 2/3 of the moles come from blue. Do you buy that? What fraction of the moles comes from red? 1/3. Now let's look at our pressure ratios. 3 moles total, 2/3 from this, and 1/3 from that. They're the same. And guys, that's the point. When you have mixtures of gases, their mole ratios and their pressure ratios are equivalent. So if 2/3 of a gas by moles is one particular component, then 2/3 of the pressure will also be attributed to that component gas. And guys, that is what this is saying. That's the whole idea behind this. The idea being is if these factor and therefore don't play into the math, then our pressure ratios and our mole ratios will be the same. Does that make sense? Okay, so guys, that's big idea number 1, and it actually gets summarized in this statement. It says the pressure of a gas contributes to the pressure that a gas contributes to a mixture is proportional to the number of moles it contributes to the mixture. That's a very succinct way of saying what we were talking about. Okay. I'll give you a second to write it down. Let everyone finish writing it, and then we'll talk. Okay, are you guys done writing? Because Anna's got a question, but I want to make sure y'all can hear it. So go ahead.
Okay, so I'm just trying to navigate the words because before we talked about ratios, and we said with their ratios, it would be equal, and now we're talking about proportional.
Hold on. Let me go to ratios. I want to look at, well, I want us to be looking at things. So let's go here and there. Can you help me understand your question relative to this picture?
Or we said like the ratio of the number of moles to the total, it would be the same as the ratio of the number, like the amount of pressure attributed compared to the total pressure.
Correct.
So that's the same proportional, that's not going to change.
Yes. Oh, so the words, you feel like we're switching words and saying the same thing. So you're saying proportional. So the sentence that I gave you, so the sentence uses the word proportional. What did you feel like we said before?
We said equal, like the ratios are equal, so I was trying to like fix it.
So what? Yeah, no. So what if we said this? So we could say it either way. So the ratios are. Yeah, no, I know, right? So we could say the ratios are equal. So we got to say which ratios. So the pressure ratios and the mole ratios are equal. So what does it then mean? Wouldn't that also mean they're proportional? In my mind, those words seem interchangeable. No, but what if we did this? So let's say we didn't know a lot about this gas. But let's say that we did this, and let's put our gas together. And then let's say that we knew this. We know that, let me pick a good color here. Let's just stay with black. So say that we have a mixture of gases, and we know that 2/3 of the moles are blue gas. Then we also know 2/3 of the pressure from the blue gas. Now let's hit the mental reset button. What if we were given a mixture of gas and they told us 2/3 of the pressure was from the blue gas? We also then know that 2/3 of the moles are from the blue gas. So that relationship works in either direction. Is that okay? Yeah, no, so could I put, yeah, no, I totally understand what you're saying. So what if so the pressure that a gas contributes to a mixture is equal to the number of moles it contributes to the mixture. Do you like that better? Because proportional takes out the variables. Okay, then I'm going to leave it like this. Okay, but you're okay? Go ahead, Brian. Correct, there would be a small difference.
Volume would be slightly different.
Yeah, yep. We good? Okay, so now guys, these are the kind of problems that you've got to be able to solve based upon Dalton's law of partial pressures. I was frightened to write this question. I wrote it before school today. If you printed the notes, there's a different question offered every year until now. I just changed it. So it says this. A sample of a gas is collected over water. At the time of the collection, the water bath had a temperature of 23 degrees Celsius and atmospheric pressure was this. What is the pressure of the collected gas? Sound familiar? So guys, we're going to solve this. So for those of you that are not in the lab, you need a context for the question. For those of you that are in the lab, you may be developing a little bit of an eye tick because you're thinking, oh boy, here we go again. But guys, the question is just like we're talking about in lab. We've got a cylinder, we collected gas in the cylinder, right? So the question is asking you this. So we've got the water in the cylinder and we understand that atmospheric pressure is 644 millimeters of mercury. Now, we also understand, and for those of you that are not in the lab, this is the part that you don't know right now. So this gas is up here inside this cylinder. But the thing you've got to understand is that is not the only thing in the cylinder. The cylinder also contains a little bit of water vapor. The water that we're displacing in order to collect the gas, some of it evaporates into the cylinder. So the question is, what is the pressure of just the black gas? Because the pressure in the gas isn't pure. It's a mixture that also contains water vapor. So guys, how do we approach solving this thing? So we've got a mixture of gases. So what equation allows us to describe mixtures of gases? P total, yeah. So we just go P total is equal to PA plus PB. That's all we need because we've only got two gases. So now guys, we need P total. What is the total pressure inside the cylinder? Well, it's atmospheric pressure because we've equilibrated the water levels. So P total would be 644 torr. What did I just do? Yeah, torr and millimeters of mercury are interchangeable. That is a really funky 6. Then guys, we need to know, oh, go ahead. Either one is fine. Yeah, you can reflexively, whichever you choose. They get that. Okay, then guys, in order to figure out the pressure of the black gas, we need to know the pressure of the water vapor. And again, that takes us to page 1058. And when we look on page 1058, we can figure out the pressure of the water vapor in the cylinder because we know the temperature of the water vapor. And the temperature of the water vapor is 23 Celsius, which tells us the pressure is 21.07 is that right? 21.07 torr. So here's what we now know. In that mixture of gas, we now know that 21 torr of the pressure is attributed to the water vapor. The remaining pressure is then attributed or created by the gas that we captured. So we could go 644. And by the way, that was actually atmospheric pressure this morning, guys. That was crazy low. So the pressure of our trapped gas then is 623 thereabouts torr. Yeah, 622.93, but remember yeah. Okay.
I need to go back to first grade, guys.
So are we okay with this idea? Now, guys, let's do this. And this isn't in the question, but let's talk about this to reinforce what you just learned. So, guys, the idea then, I'm going to write up here and switch colors. Here's what we now know. We know that, we'll do it this way. 623, oh, that's not a 2. So 623 torr are attributed to our collected gas. I'm going to round. 21 torr are attributed to the water vapor. But the total pressure is this. So now we can do some, and again, this isn't in the question, this is all bonus thoughts. 623 divided by 644 is about, I'm going to call it 90, so it's 0.97, and then 21 divided by 644 is 3. So guys, here's what we now know. By moles, 97% of the gas in that cylinder is whatever our gas was, and 3% of the gas in that cylinder by moles is water vapor. You get the idea? But again, guys, those are not by mass, those are by moles. But again, the connecting thought is, if we know the pressure ratios, we also then know the molar ratios, which was the point of what we just learned.
This would be a wonderful free response question.
Yeah? And as a matter of fact, guys, I want to include that because that's an interesting follow-up. So, by moles, what percentage of the gas, of the gas is water vapor? All right, by moles, what percentage of the gas is water vapor, and what percentage is collected gas? Go ahead. Yes. Yep. Does that make sense? Is that cool? You guys good? Okay. So now, guys, here's what we're going to do. We're almost done. So, guys, what we're going to do to wrap this up is we are now going to take that idea that you just had. So maybe we should go back. Guys, we're going to take this idea that we just had that says our pressure ratios and our mole ratios are the same. We're going to take this idea and we're going to recast that reality in a simple equation that will allow us to actually answer this question more quickly. So the additional question that we had, which says, by moles, what percentage of this sample is water and what percentage is collected gas? Because there's a way that we can focus and recast these relationships that make answering that question much easier. And you do this through what are called mole fractions. So guys, you're probably going to want to scratch this in your notes. Well, no, I wouldn't, you know what, let's don't. I really think you're going to be fine right up till I give you the equation, which is already, let me step you through this. So, we should be okay with this idea. The gases in mixtures behave independently. And because of this, we can look, and whether you like equals or proportional, we can look at pressure-mole ratios. So guys, here's how we do this. We're going to take Pivnert and solve for P, okay? Now guys, watch. So, and I'm going to do this digitally. It might be better to write it out. We'll see as we go. So here's what we're going to do. We are going to look at pressure ratios and mole ratios. And again, it's just a retelling of what we said, whether you like the word equal or whether you like the word proportional. The idea is this. We are now going to look at a pressure ratio, which is the pressure of any component gas and then the total pressure of the gas. So guys, that ratio is, from the previous question, this ratio. You see it? Pressure of A, pressure total, pressure B, pressure total. Good? But all that we're saying, guys, is that that ratio is actually equal to this. So here's what I did. I took Pivnert and solved it for P. So we have nRT divided by V. So P is equal to nRTV and P is equal to nRTV. Now guys, do you see where this is going? What do we know about the R's? They're the same. What do we know about the T's? What about the V? Yeah, so guys, these cancel out and look at what we're left with. All we're doing is showing mathematically that what we just did in the previous problem is true. It's basically saying if we know the pressure ratio, we know the mole ratio, and if we know the mole ratio, we know the pressure ratio. Get the idea? But guys, the interesting bit then is this. This has a name. Look at it on your equation sheet. You see it there? If you look at the second equation down under gases, it's interesting that, typically they define the variables in the right-hand column. Here they defined it right in the equation, which is kind of handy in this example. Because it says, do you see where I'm reading? Where XA is equal to moles A divided by moles total. So guys, that's this, right? Moles of A divided by moles total. We actually call this X sub A. Yeah? Yeah, so that entire fraction is equal to X sub A. But then, guys, look at what we can do. We can solve this for pressure of A by simply cross-multiplying. And when we do that, and I'll do that in front of you right now digitally, so guys, we understand that this N sub A is equal to X, or I'm sorry, NA divided by N total is equal to X. So we end up with this. X sub A, but I substituted, and then we can just cross multiply, and when we cross multiply we get this. And what it's saying is this. It's saying the pressure of any component gas is equal to the total pressure times the mole fraction of that gas. So if 2/3 of a gas by moles is something, then 2/3 of it by pressure is that same something. Does that make sense? So guys, we can now apply this to problem solving. But first of all, let's link it to the equation sheet. You guys all see it? So it says the pressure of some component A is equal to the pressure of the entire system times the fraction of that gas by moles, which is made up by A, because pressure ratios equal mole ratios. Good? Okay, so let's solve this. I frankly don't remember where I got this question. It may be out of the book, but anyway, it says, from data gathered by Voyager 1, which I think is still out there doing its thing, scientists have determined the composition of the atmosphere of Titan, one of it's Saturn's largest moon. So the total pressure on the surface of this moon is this. Is that higher or lower than our atmosphere? Almost twice. Ours is 760, right? So 1500 would be about twice. So it says a 5 mole sample of this moon's atmosphere is found to contain 4 moles of this, 0.6 moles of this, 0.3 moles of this. What are the partial pressures of these gases on Titan? So how do we solve this? Well, but guys, remember we need equations. To solve something mathematical, you need equations. I like that you're thinking through it logically, but we have to tie that back to equations. So you get presented, and this may be off of an AP test. I don't frankly remember. But guys, regardless, how are we going to solve this? What equation are we going to use? We're going to say P sub A is equal to, how do they write this on the equation sheet? P total? Yep. P total times X sub A. Now what are we solving for? Well, it's asking you for the partial pressures of these gases. That would be P sub A. What is the pressure total? 1220 torr. And then guys, we need to know X sub A. So, exactly, you're gonna have to solve this 3 times. So, we know that the total moles is 5. Guys, what if they hadn't told us that it was a 5 mole sample? You just add up all the moles. 4.1 plus 0.6 plus 0.3 is 5 moles. So, we know that the total moles is 5. And then let's do this for whatever our first gas is, which is nitrogen. So that would be 4.10 moles. So guys, we now know that 82% of this gas by moles, right? 4.1 out of 5. 82% of this gas by moles is nitrogen. So what is it going to be pressure-wise? 82%. So 1220 times 4.1 divided by 5, which is functionally 82%, works out to really close to 1,000 torr. Is that what you got as well? Is that right? Yep. Okay. And then as Brandon pointed out, you would just have to solve this again for gas 2 and then again for gas 3. But the idea being, coming back to the concept that if we understand our mole ratios, we understand that mole ratios and pressure ratios are equivalent. Is that okay? We done. So guys, we have got about 15 minutes, which we're going to spend working on homework, whether you want to or not. We're going to do 6, 7, 63, 67, 69, 73. Grab some paper. We've got about 15 minutes. Spend your time well. Go get them.